Okay. Uh, okay, shall we start?
Sure.
Just a moment. Okay. Okay. Hello everyone. Welcome to the 8th session of the ISRM Young Members Seminar Series. And my name is Kyota Hashimoto from Hiroshima University, Japan. And Dr. Lina Goyakin from École de Pont Paris, France. And I happy to chair this 8th monthly seminar as part of the ISRM Young Members Group. And it's a great pleasure for us to be here today, and we would like to thank you for attending this 8th session. Before starting, we would like to thank the support from the International Society for Rock Mechanics and Rock Engineering, and especially to Sevda Decoda, ISRM Vice President for Australasia and Chair of the ISRM Young Members Committee. We also would like to thank all young member representatives of national groups that have joined this initiative. Finally, we would like to thank Dr. Wei Li and Dr. Hafsa Tunsi for agreeing to present their work in this session. Before our speakers begin, we will take a moment to present key information about the seminar series. This project attempts to promote youth community interested in rock mechanics, including engineers, research scientists, and students, to foster knowledge in rock mechanics among this community, to share experience both in the industry and the academia, and to strengthen relations between different countries. We would like to invite a variety of young members to participate in this seminar series. The criteria for the speakers are as shown here. So being an ISR member and having a maximum age of 35 years or of 40 years if a PhD degree was obtained in the previous 5 years. Then having worked in rock mechanics and rock engineering for a period no longer than 10 years. Speaker nominations can be made by the nominees national group or by some other person or organization acquainted with the nominee's work. Self-nominations are also accepted. Nominations are to be addressed to the ISRM Young Members Seminar Series Organizing Committee. On the screen, you can see our contact email. So this webinar will be held every month. So we invite you all to keep in touch. We will now begin the first presentation today. And each presentation will last 20 minutes and will be followed by 10 minutes of Q&A session. And for the smooth running of the seminar, please turn off your camera and microphone during the presentation. And if you have any questions, you can use chat and also the raise hand feature from the reaction button. Okay, now we would like to start the first presentation. The first speaker is Dr. Wei Li, who is currently working as an assistant professor at the New York State University at Stony Brook. He obtained his PhD degree in 2019 under the supervision of Professor Herbert H. Einstein at MIT. And he then worked as a postdoctoral researcher with Professor Ruben Juanes at MIT. He's strongly interested in the geosystems centered on infrastructure and energy. And today he will be presenting a talk entitled 4D computed tomography of granular force chains. So now, Dr. Lee, please start your presentation.
Thank you. All right, everyone, can you see my screen?
Yes, I can see.
Okay, great. Let's get started. Thank you, Ryota, for your kind introduction. Hello, everyone. My name is Wei. I'm currently an assistant professor in the Department of Civil Engineering at Stony Brook University. In today's seminar, I will present a new type of tomography called 4D computed tomography of granular force chains. This work is done in collaboration with Professor Ruben Juanes in the Department of Civil and Environmental Engineering at MIT. In today's talk, I will first introduce you a new type of method called photopore mechanics that visualizes effective stress. This is a two-dimensional method, two-dimensional experimental method. And I will move on from 2D to 4D to visualize the force chain evolution in three-dimensional granular media. So why do we study granular media? Granular media is the most abundant form of solid matter on Earth and beyond Earth. It supports our infrastructure shown on the railway track, and it supports our space explorations, such as the first step on the moon. However, the failure of granular media could lead to devastating consequences, such as landslides and earthquake. The behavior of granular media is very complex. It could exhibit gas, liquid, and solid-like behavior when they are dry, and coupling with fluid. Sorry? Okay, coupling with fluid, it will exhibit even more complex behavior, such as gas invasion and gas fracturing. One of the pioneers in this study is Professor Robert Beringer at Duke University. To visualize the interparticle forces that drives the behavior of granular media, they use photoelastic disks to mimic two-dimensional granular media. And these disks light up when they are under forces. So when they pack it together, you will be able to see the interparticle forces showing like this, this force network. Another type of study was done by Professor Jose Andres' group at Caltech. They use particle tracking and DIC to visualize the deformation on each of these particles. And from the deformation, they can calculate the interparticle forces. And their findings are similar. The forces are transmitted in granular media through force chains. Well, powerful as this method can be, what about fluid coupling? More importantly, what about effective stress that governs the behavior of granular media when they are coupled with fluids? Can we simply put these methods in underwater and visualize effective stress? The answer is no, because effective stress, this is a very important concept that was introduced about a century ago by the father of solid mechanics, Carl Zagi. The concept is relatively simple. If you imagine you apply a certain load on soil, the soil will not deform immediately. But if you allow the pore fluid to drain, the pore pressure to dissipate, the soil will further deform. So from Kawasaki point of view, effective stress is the total stress minus the pore pressure, because the pore pressure is supporting part of the load, right? And the effective stress governs the deformation and failure of porous media and granular media. Important as this concept is in the field of civil engineering and geomechanics, effective stress has never been directly visualized or measured. And this is what our new technique does. We call this new technique photopore mechanics. The previous method, as I discussed, they use disks, right? The pores among these disks are not connected. So they are not forming a proper analog of a porous media or granular media. So we have to use three-dimensional particles. These particles will allow pore connection and thus pore mechanical coupling. Only with this proper analog can we study effective stress. So that's what we did. We make these photoelastic spheres and angular particles that are three-dimensional. So when we pack them, they will have pore connection. So this angular particle we fabricated is called icosahedral. It's a three-dimensional shape that has more angularity for interparticle locking. These particles are photoelastic, and at the same time, they are residual stress-free. Well, what is residual stress? If you remember what the ruler looks like under white light, this is what it looks like under cross-polarized light. You can see the color fringes. We don't want that, right? We want our particles to only show up color and brightness change when they are under stress. And we did that because you can now barely see these particles. And here is how the particles behave. This is my hand squeezing these particles. They light up when you squeeze. And if you squeeze them really hard, you can see the column fringes. And these particles are also chemically compatible with many fluids such as oil, water, glycerol, and air. And even when there is multi-phase flow interfaces, it does not affect their behavior. So besides playing with these particles, we conducted calibration tests. We load these particles in steps and record their reaction forces and the brightness change on these particles. And after we associate this, the brightness with the forces on them, so that we can quantitatively analyze the local stresses on these particles. So with this calibration test, each of these particles will be a local indicator for the forces. And here is a classic experiment done using our technique. This is a consolidation test. We pack these particles into a monolayer cell. We saturate them with high viscosity oil, and we will apply a sudden load onto the piston. And here is the experimental result. So what you are looking at is a real-time video of a consolidation experiment. After the sudden application of the load, the pack did not deform immediately. However, it deforms only as the pore fluid dissipates. And if we take a look again, you can see that the particles start to light up, indicating that the effective stress start to develop in the pack, at the top of the pack, and then it starts to propagate down. That means the effective stress starts developing at the top. That's also the place where pore fluid starts to dissipate. So qualitatively, you can already see that this is consistent with the 1D consolidation theory. Now, here is a more quantitative study. We take 6 snapshots during the experiment. we average the light intensity horizontally. So we have a vertical profile of the light intensity. If the light intensity is indeed indicating the effective stress, we should have a good match with the 1D consolidation model, which is shown in dashed line. And here you can see that the experimental results match the model pretty well. So now we can confidently say that we are able to visualize and measure the effective stress for the first time in porous media. Now, we immediately apply this method in the study of gas invasion in fluid-saturated granular media. You know, when the particles are fully saturated, they could behave like a solid or a fluid. When they behave like a solid, the fluid has to permeate through the pores. But when they behave like a fluid, they can just flow together all together with the pore fluid. So it is really hard to tell from traditional methods, but now with photopore mechanics, we can easily tell, right? So this is an experiment when we inject the air into a fully saturated pack of photoelastic particles. And as you can see at the tip of this fracture, the granular media behaves more like a solid where you can see effective stress. And behind the tip of the fracture, it behaves like a fluid where there's no effective stress. Another type of experiment is when we cement all these particles, and now this is no longer a granular media but a porous media, right? It could undertake tensile stresses, and this is another example when we inject water into oil-saturated porous media, and you can see these force chains that are circular around the injection port, indicating that there is negative stress. Negative stress meaning tensile stress. So now I have presented a new technique that can help us visualize effective stress. But how about three-dimensional granular media? Well, there have been several studies. What they do is they use either index matching tomography or X-ray CT to reconstruct the deformation on each of these particles. And then based on this deformation, they use force balance, contact models, and constitutive models altogether to calculate the interparticle force chains like this. This is how forces are transmitted through three-dimensional granular media. Now we want to come up with a new method that does not need to assume contact model, and it can do particles with more angularity. So we learned from tomography that we should use a penetrating wave to generate a 2D projection of a 3D object. For example, this is a first X-ray of a hand. And then when we rotate these 2D when we rotate the object while we generate these 2D projections, we can reconstruct the three-dimensional model of the based on these 2D projections. So this is what we did with our new type of tomography. We want to integrate photoelasticity with tomography. However, one big obstacle is that these particles at the same time are lenses that cause refraction of the white light. We don't want that reflection, right? We want the white light to be the penetrating wave. So what we did is we make this index matching fluid with these particles. And now when we saturate these particles with this index matching fluid, you can see they no longer refract the light because it got canceled out. So now we can use white light as the penetrating wave. And here is a schematic of the setup. White light generates through this night panel, and and it penetrates through this index matching fluid tank and this three-dimensional pack of particles. And then we can generate these 2D projections. And here is how the setup looks like. This is a setup to apply normal stress and rotary shear onto the three-dimensional pack of photoelastic particles. And this is the index matching fluid tank. This is the rotation stage that rotates the pack. And here is how it looks like under cross-polarized light. And you can already see some filamentary patterns using this technique. And here's a close-up of the loading device that applies normal stress and shear stress onto the pack of photoelastic particles. And again, here's a conceptual design. White light penetrates through this index matching fluid tank and the three-dimensional pack and got recorded by the camera. And so here is the 2D projection. And this is a 360-degree rotation of the 2D projection. And as it rotates, we take pictures. And this 360 rotation, we take about 2,000 images to reconstruct the three-dimensional fortune. And here is how it looks like. And this is the first time we see helical-shaped fortunes in granular media. Now, this is another type of experiment where we apply confining stress and vertical stress onto this three-dimensional pack. And here are the load steps. We apply a 2.7 kPa of confining stress, and we increase the vertical stress to about 5.6 kPa. As we increase this vertical stress, the pack starts to deform and light up in the same time. And you can see these filamentary patterns also show up during the loading. And this is when the pack fails. And based on the tomography, we can reconstruct the three-dimensional force chains that developed in these packs. We can see that the force chain starts to line up with the vertical direction. This is where the maximum principal stress direction. And this is another example using icosahedral. And with this more angular particles, you can see the force chains starts to form this clustered network that are stronger than the vertical chains that formed in the spherical particles. Obviously, particles with more angularity fails later than the particles with less angularity, these spherical particles. And we also did quantitative study trying to see how these particles, their orientation, their length, and their stress. So this is a two-dimensional histogram of their length, their stress and dip. This dip, the 90-degree dip means they are vertical. And the bottom ones are the length and stress. As you can see, when we increase the vertical stress, we will see more and more force chains that has a 90-degree dip. They are vertical, and we can also see more and more vertical and long force chains form as we increase the vertical stress. And right before they fail, the force chains start to shift from vertical to other degrees, meaning they are buckling. And after they fail, the force chain starts to disappear. So with this technology, I would like to summarize our study here. We developed a new technique called photopyromechanics to visualize and quantify effective stress in fluid-filled granular media. And we developed this 4D force chain tomography, and we found that the force chains orient along the direction of the maximum principal stress and intensify as the stress increases. And the force chains will buckle before shear failure. I would like to stop here, and here is a reference for our previous study on photopore mechanics. This study was sponsored by NSF, and we are grateful for their support. And I would also like to invite all the audience to help me recruit new students. I have 2 fully funded research assistantship, and you can contact me through my email or visit my website to see more details. Stony Brook University is a really nice university located on Long Island. It's a great place to study granular media, and it is also associated with the Brookhaven National Lab, where there are really nice devices and equipment for us to study. So I would like to stop here and give the stage back to Ryota. Thank you so much for your attention.
Thank you very much, Dr. Lee, for the interesting presentation. And now we have 10 minutes for the question and answer session. So does anyone have any questions or comments? If you have any question, you can write on chat or you can start speaking. Okay. Can I ask a question? Would you show the slide 11?
Okay. Slide 11. Yeah.
Yeah. I couldn't catch how can you convert the how can you get the effective stress value from
so there are 6 snapshots during the consolidation experiment. What we did is we averaged the light intensity horizontally, right? So you will have a vertical light intensity profile as indicated by the solid curve here. These profiles are normalized. The light intensity is normalized by its maximum light intensity, which is here. So you will always reach 1, right? Because you know in the end of the consolidation, the effective stress is the applied stress. So same goes for the light intensity. And the key here is to use this normalized light intensity to track the evolution, right? So the normalized light intensity will evolve as such, right? As indicated by these solid curves. And if the normalized light intensity is indeed effective stress, it will match the prediction of the 1D consolidation theory, which we find could match here. So that's how we confirm that our technique is indeed visualizing the effective stress.
So the relationship between the intensity and the stress is already calibrated in other experiment or something.
So in the calibration experiments, we establish that in a certain range of stresses, the light intensity should be proportionally, like linearly related to the applied stress. So after we establish this linear relationship, when we normalize everything, it will be exactly the same, right? So that's why we normalize the light intensity, and here is also the normalized effective stress.
Okay, thank you. Is there any other questions? we still have 5 minutes for Q&A.
I think we can move on.
Okay.
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 So thank you, Dr. Lee, for your presentation. Let me introduce the next speaker of this webinar session, Dr. Tunsi. She grew up in Morocco, where she got her civil engineering degree from Hassania School, Casablanca, followed by a Master of Science on Soil and Rock Mechanics at the École de Pont Paris-Tech. After that, she did a PhD at the Geoscience and Geoengineering Department of Mines Paris-Tech. Currently, she is a postdoctoral researcher at Lawrence Berkeley Lab. Her scientific interest is in developing and applying coupled thermo-hydromechanical and chemical modeling to geoengineering applications such as geological sequestration of CO2, the use of artificial ground freezing for the exploitation of complex mineral deposits, or for subsurface ice storage and geological disposal of radioactive waste in salt formations. Today, she will be presenting a talk entitled Coupled Thermo-Hydromechanical Modeling of Radioactive Waste Disposal in Rock Salt. So, Hafsa, the floor is yours.
So thanks, Lena, for the introduction. Hello, everyone. My talk today is about coupled thermohydromechanical modeling of radioactive waste disposal in rock salt. This is a subject that I am currently working on at Lawrence Berkeley National Lab under the supervision of John Rudqvist. So the disposal scenario we investigate consists of emplacing waste packages inside horizontal drifts that are excavated in rock salt and then backfill them with crushed salt. We have identified several thermal, hydraulic, and mechanical processes associated with this disposal scenario. And among them, we have in the short term, the development of a damaged zone around the newly excavated drifts, the compaction of the backfill, the healing of microfractures in the damaged areas, and finally, the increase of temperature in the repository and the resulting pore pressure buildup. So to investigate these processes and their impacts in the short and the long term on the integrity of the geotechnical and the geological barriers, we use a macroscopic numerical modeling approach, which I will briefly present. This approach has been validated against different lab and field experiments in order to use it confidently for the simulation or the prediction of the behavior of the salt repository for high heat emitting nuclear wastes. In all the simulations I will present in my talk today, the TUF FLAC simulator was used. It links TUF, Berkeley Lab in-house simulator for multi-phase flow and heat transport with the geomechanical code FLAC3D. So the energy and mass balance equations are first solved in TUF, and then the mechanical problem is solved in FLAC3D using the newly computed values of the pressures and saturations of the different phases in the pore space and temperature. And the mechanical calculation allows to update the grid because we are in the large deformation framework in order to accommodate the large deformations of the backfill during reconsolidation. So the grid is updated using the newly computed values of the strain tensor, and the flow parameters are also updated, such as the porosities and the permeabilities. To describe the mechanical behavior of rock salt, we use the Lux-Walters model. It has been developed by our collaborators from Clausthal University of Technology. In this model, the total strain rate tensor is decomposed into an elastic component, a viscoplastic component that includes transients and steady state creep, and their evolution laws are a function of deviatoric stress and temperature. The third one is the shear-induced damage that takes place when the shear or the von Mises stress exceeds the shear strength, which is a function of the minimum principal stress and the load angle. The appearance of tensile stresses also leads to additional damage. And the last component is the healing one due to the increase of confining pressure or the closure of microfissures. So when thermomechanical damage takes place and the volumetric strain exceeds a dilatancy threshold, then the preformed microfractures start to coalesce, leading to an increase of permeability. So we take into account this increase of permeability. It is also a function of the effective stress perpendicular to the direction of the microfissure. Permeability can also increase due to hydraulically induced damage that happens when the fluid pressure exceeds the minimum principal stress, which leads to an infiltration of the saturating fluid along the newly opened grain boundaries. We consider also the increase of the BO coefficient with damage. And we use two empirical expressions to describe the variation of the thermal conductivity and heat capacity of rock salt with temperature. For the backfill material, crushed salt, we use a modified version of the CWIP model. In this version, the total strain rate tensor is decomposed into an elastic component. The drained elastic moduli now evolve with crushed salt density. So when crushed salt density increases, the bulk compressibility increases and the BO coefficient decreases. We have a second component, which is the viscous compaction strain rate tensor. It has a deviatoric and a volumetric component, and it depends on the mean stress and density. It becomes equal to 0 when the density of crushed salt reaches the density of natural salt. The last component is the viscous one. It is purely deviatoric. It depends only on the deviatoric stress and temperature, and it does not get cancelled when the backfill is fully reconsolidated. It has a transient and a steady state components, which are expressed in a similar way to the WIP model, also implemented in FLAC 3D. Permeability and thermal conductivity of crushed salt are assumed to vary with the porosity. So when the porosity of crushed salt decreases, its permeability decreases as well. But it can increase again in case we have hydraulically induced damage when pore pressure exceeds the minimum principal stress, like for rock salts. So as I said in the beginning, this model has been validated against different lab and field experiments. Today, I have chosen to show the example of an experiment that was conducted in 1980s by Sandia National Laboratories, but it has never been properly modeled. So this experiment was carried out on a salt block of 1 meter in diameter and 1 meter in height. A borehole was drilled from the top center of the borehole, and a heater was placed in this borehole. Then the salt block with the borehole and the heater was placed inside a gas-tight stainless steel jacket with cooling coils in the outside circumference in order to maintain the temperature equal to the initial temperature, 20 degrees Celsius. This test lasted more than 4 months and comprised 5 heating stages and a shutdown phase during which the heater power was decreased in a stepwise manner as well. Temperature was measured in different locations of the salt block, the black circles, and dry nitrogen gas was circulated inside the borehole and periodically collected in order to measure the brine inflow into the borehole. So the figure in the top left shows temperature measurements and predictions in a location at the middle of the salt block near the borehole wall, TC11. So as you can see, temperature during the last heating stage reaches 180 degrees Celsius, which is comparable to the temperature we would expect in a salt repository. The agreement between the measurements and the predictions is satisfactory both during heating and cooling, except for some brief variations of temperature due to power outage events that we have not simulated. To the right, we have the evolution of the inflow rates into the borehole during the experiments. As you can see, we have a spike of brine inflow each time the heater power was changed. During heating, the magnitude of this spike increases with the heater power, but the highest spike is obtained during cooling when the heater power was decreased. During heating, the main mechanism controlling the magnitude of the inflow rate spikes is thermal pressurization due to the thermal expansion of salt and brine, which leads to an increased pressure gradients in the salt block. But during cooling, another mechanism takes the lead. To explain this mechanism, let's have a look at the evolution of the minimum principal stress during the experiments. So as you can see in two locations, 7 centimeters and 17 centimeters from the center of the borehole. So both locations are under a compressive stress state during heating, and we have small spikes of stress when the heater power is changed. And the magnitude of the spike again increases with the heater power. But during cooling, the two locations become under a tensile stress state, and the magnitude is far much higher than what we have during the heating phase. And since the tensile strength of rock salt is low, around 1 megapascal, then the salt block, due to cooling, becomes damaged and microfractured. And when this damage exceeds a certain limit, the permeability increases, which explains the increased inflow rates during cooling. Obviously, those results cannot be obtained using a thermopore elastic framework without considering the creep of rock salt and the damage that results from the variation of temperature. The fact that we are able to reproduce such experiments gives us more confidence in using our model in order to study the behavior of rock salt repositories in the short and the long term. So now I present some key results from our simulations of a generic salt repository using the 2D geometry you see here. To build this geometry, we considered repetitive symmetries of the horizontal drifts and the plane strain assumptions. So we end up modeling half of one drift excavated at a 600 meters depth in the middle of a 400 meters thick salt formation. And the width of the model, equal to 25 meters, corresponds to half the spacing between the emplacement drifts. We assign to the waste package this decay heat function, which corresponds to a large-sized canister containing up to 37 power water reactor elements, emplaced 100 years after 100 years of interim storage, and it's calculated for a spacing of 20 meters between the waste packages along the drift. So we simulate first the excavation of the drift, the emplacement of the waste package and the backfilling in order to generate the initial pore pressure and stress fields. And in the next slides, I'll present the results for the post-backfilling stage. So let's start with the evolution of porosity in 3 locations inside the drifts and in the host rock near the drift wall. As you can see, the porosity in the backfill is initially equal to 30%, and in less than 20 years, it becomes nearly equal to the porosity of natural salts. This quick reconsolidation of the drifts is of the backfill is due to the drift closure, due to the creep and dilatant behavior of rock salts around the drift under the excavation-induced deviatoric stresses. The high creep rates in rock salt around the drift are also due to the high temperatures in the repository. So this figure shows the evolution of temperature in 3 locations of the repository. In the 3 locations, temperature exceeds 100 degrees Celsius over thousands of years. Even in the green point located 25 meters away from the drift wall. And we have a first local peak reached 1 year after the backfilling, only in the vicinity of the waste package due to the low thermal conductivity of the backfill before compaction takes place. And we have a second long-term peak reached 800 years later in the 3 locations. So as the backfill reconsolidates, the elastic moduli of crushed salt tend to the elastic parameters of rock salt, and the initial or the stress state, which is initially equal to 0 in the drift, increases and becomes equal to the initial undisturbed isotropic stress state in the host rock. Now, I'm showing the distribution of shear dilatancy around the drift in order to get an idea about the extent of the excavation damage zone around the drift. So as you can see, 10 years after the backfilling of the drift, the shear dilatancy reaches its peak, its maximum values, and it's around 2.7% in the corner. The damage zone extends 1.4 meters on top of the drift and below the floor, and 1 meter around the side walls. We have also some tensile dilatancy, but it's very localized in the floor corners and the center of the roof, and is probably due to geometrical considerations. And then we have the distribution of healing. So as you can see, at 10 years, the healing becomes significant, which explains why the shear dilatancy and tensile dilatancy reach their maximum at this date. But 10 years later, the excavation damage zone becomes fully healed, and this quick healing is accelerated by the quick reconsolidation of the drift. So the main outcome from these dilatancy maps is that the creep and dilatancy of natural salts trigger and accelerate the reconsolidation of crushed salt, which in return contributes to the acceleration of host rock healing. The hydromechanical coupling in the EDZ, or the excavation damage zone, is very strong. Those maps show the evolution of the biocoefficients in the EDZ. So as you can see, at 10 years, when the dilatancy is maximum, the biocoefficient can even reach the value of 1 in the corners and near the side walls. But thanks to healing, its initial low value is restored 10 years later. The permeability in the EDZ also increases up to -17 to the power of 10 in the first years, but its initial value is restored as well, thanks to healing. So as I said in the first slides, the shear and tensile dilatancy are not the only mechanisms responsible for the increase of permeability. We have also the hydraulically induced damage. To investigate this process, let's have a look on the pore pressure and liquid saturation evolution in 3 locations. So in the host rock, the green point, the pore pressure is initially equal to the hydrostatic pressure. And in the drift, it is equal to the atmospheric pressure. So since the host rock is fully saturated, thermal pressurization is significant, and it starts to increase first due to thermal pressurization. But as the backfill reconsolidates, liquid saturation inside the drift increases, and the pore pressure or the thermal pressurization becomes significant, and pore pressure increases as well. In the three locations, the pore pressure exceeds the lithostatic stress level indicated with the purple line, and this induces an increase of permeability and a decrease of pore pressure until it stabilizes around the lithostatic stress level. And when the temperature starts to go down, the pore pressure starts to go down as well. In order to investigate whether we can alleviate this strong thermal pressurization in the repository, we have conducted another simulation where the spacing between the emplacement drifts has been doubled. This figure shows the old results of temperature and the new ones represented with dashed lines. As you can see, the long-term peak of temperature significantly decreases when the spacing was doubled. Now let's see the effect on pore pressure. So in the host rock, pore pressure reaches its peak and then decreases and stabilizes at a pore pressure level below the lithostatic stress. So increasing the spacing was kind of beneficial in the host rock. But at the drift wall, the pore pressure is still exceeding the lithostatic stress level, even when the spacing was doubled. So to sum up, we have seen that the salt repositories behave in a highly THM coupled manner. The simulations have shown that the high temperature changes and quicker consolidation of the backfill induce a strong thermal pressurization that may not be avoided even in the case of a large distance between individual waste packages and emplacement drifts. However, there are still some uncertainties related to crushed salt compaction rates. There is some recent experimental data on the compaction rate of crushed salt that suggests that this compaction rate will decrease with the decrease of porosity, which would result in a longer or a slower reconsolidation of the backfill. Also, the deviatoric stress in the repository in the long term is lower than 1 megapascal, and most creep data available in the literature is conducted or carried out in a large deviatoric stress range. So low stress creep data is needed for a better calibration of constitutive models and a more accurate prediction of the long-term behavior of the repository. So that's it. Thanks for your attention, and I would be happy to take your questions.
Thank you very much, Hafsa, for this interesting presentation. So now we have 10 minutes for the Q&A session. Does anyone have any question? So I think I can start. In your slide 6, you present. Yes, you present that the model reproduced very well the spike, but I see that the spike are shift or some days. There is an explanation for that, or maybe it's the representation.
What do you mean shifted? Where?
There are some the spikes that are not in the same, in the same point. There are some days shifted in the simulation.
Okay. Yeah, it's because for the constructing this curve of heater power, this is a schematic curve. We don't have the exact measurements of the heater power with time. We have, it's a very old experiment, so we have events. we know that after 10 days, the heater power was increased. But this is a modeling. This is schematic. It's not we don't have the real curve showing the exact heater power value with time. So this is an approximation of the heater power. We only have dates, the dates when the heater power was increased or decreased, but we don't have. So it's maybe due to that.
Okay, thank you. So there are questions? No? Okay, I have here another question about the effect that the slow compression of the crucial salt backfill will have on the repository behavior.
Yes. So the slow compaction of the backfill would have an advantage and a disadvantage. The disadvantage, I would say, would be the slow reconsolidation of the backfill, which means that the waste package would be in contact with a geotechnical barrier that is not completely impermeable during probably thousands of years. And the advantage would be the alleviation of the strong thermal pressurization, because the reconsolidation will be very slow and the increase of the liquid saturation inside the drift will be very, very gradual. So we would avoid the problem of thermal pressurization in the repository.
Thank you, Hafsa. So we have another question in the public. No question. Okay, I have a last one. About the view coefficient, then you show a value about 0.003.
Yes.
It is a very, very small coefficient. I don't know what can you say about this value?
Traditionally, for rock salts, in the salt community, the BO coefficient for rock salt was considered to be negligible. And there are very, very few experiments where the BO coefficient or the measurements of the BO coefficient of rock salt was attempted, because it's this rock has a very low porosity and permeability. It's viscoplastic. It's difficult to characterize the BO coefficients of rock salts. I know that there are some recent works or papers where the measurements of the BO coefficients was attempted, but we cannot know if the rock salt is already damaged in these experiments, because they show that the value of the BO coefficient is probably around 0.1 or 0.2, but the BO coefficient was measured sometimes near the dilatancy boundary to make it easy to measure, so it's probably already damaged. And also in our modeling approach, we simulate the evolution of the BO coefficient with the damage. So in these recent works, the value of the BO coefficient is not correlated with the damaged state of rock salt. So we cannot use them for the moment. So we just assume, it's a hypothesis, that initially rock salt is not disturbed, so the BO coefficient is very low, and as the rock salt gets damaged, the BO coefficient increases, and we just use a lower bound of the BO coefficient. It was calculated by Zimmerman in a very old paper. It's the function of the porosity and the Poisson coefficient, or just the porosity as a simplification.
Okay, thank you. So thank you very much, Hafsa. We are now at the end of this 8th ISRM job member seminar. On behalf of the organizing committee, I'd like to thank the ISRM for helping us in the organization of this event. We would also like to thank Dr. Lee and Dr. Tunsi for their very interesting and valuable presentation that addressed two relevant topics in rock mechanics and rock engineering. We hope that this seminar provides you new insights and new challenges for future research, and it could be a periodic event for sharing ideas about rock mechanics and related topics. For this reason, we want to invite you for the next seminar that will be virtually held in September. Dr. Alexandro Baleta and Dr. Anuradha Kedwal will present their works respectively on deformation analysis and monitoring in underground construction, automatic system to measure convergence and pre-convergence effect, and introducing CSM 2020, discrete event simulation model for predicting tunnel boring machine utilization. Further information about this event will be available on ISRM newsletter and website, so keep in touch not to lose the next webinar. If you are interested in participating, please contact us by email at isrm.ym.seminar@gmail.com. Thank you for your participation and have a wonderful and safe day. Bye-bye.
Bye.
Thank you. Bye.